Hi Lana, I welcome you on board to this session. The topic of this session is atmosphere and altitude. It is entitled to the subject flight mechanics. The target audience for this session are GATE aerospace aspirants, aerospace and aeronautical engineering students. Let's get an outline of this session. In this session, we will be learning about layers of atmosphere and significance of individual layers under the topic atmosphere, and we will be learning about geometric altitude, absolute altitude, and geopotential altitude under the topic altitudes. Getting to know about atmosphere, let's know what is atmosphere. Atmosphere can be defined as the layers of gases which are held together by gravity of celestial body or a planet. Specifically, we are mentioning the Earth over here. It plays a major role in deciding the category of the aerospace vehicle. As we know, if the aerospace vehicle operates within the atmosphere, it is known as aircraft, and the aerospace vehicle which operates beyond the atmosphere is known as spacecraft. The major composition of atmosphere is air. What is air? Air is a mixture of gases that makes up the Earth's atmosphere. The mixture of gases is in particular composition. Earth's atmosphere has air in this particular composition. Like we have nitrogen of about 78% and mixed with oxygen of 21% and other gases in minimal amount. And we do have trace gases that is neon, helium, methane, krypton, and hydrogen, as well as water vapor in small amounts. Earth's atmosphere is generally divided into five layers. So each layer ranges between some particular range of altitude. So here we can see that troposphere ranges between this altitude and significantly we can see that every layer ranges between some kilometers. So let's get to know about these layers as they play a major role as basics and we need to know about these layers in order to answer the questions the further part of flight mechanics. So troposphere. Troposphere, as we can see here from the diagram, it ranges from the surface of Earth that is considered to be 0 kilometer to about 12 kilometers. And troposphere is the lowest layer of atmosphere and it contains about 80% of Earth's atmosphere's mass. Conventional aviation activities are carried out in this layer. Uh, by conventional activities or conventional aviation activities, I mean the typical commercial aviation and other kind of helicopter and flying drones, aerobatics, and so on and so forth. The next layer of stratosphere ranges from 12 kilometers to 50 kilometers. It has a significant property as the temperature remains constant between few ranges of this layer and the temperature is constant. Similarly, it is free of clouds and turbulence. So, airliners do prefer this layer and they do fly in the lower regions of this layer. And the stratosphere is also the highest layer where jet engine powered aircrafts can fly. As beyond this, the atmosphere grows thin and it cannot support air breathing engines. The next layer of atmosphere is mesosphere. Mesosphere ranges from 50 km to 80 km range. Mesosphere is the coldest layer of atmosphere and as the temperature change is huge, the meteors or small kind of stones, space stones, fly over this region and they get burned off. Typically in this region we could see the sounding rockets and with the balloons. Thermosphere. Thermosphere is the next layer of atmosphere which ranges between 80 kilometers to 700 kilometers. Thermosphere is where the International Space Station orbits within the range of 350 to 420 kilometers. Beyond the thermosphere, the layer of atmosphere is named as exosphere. In exosphere, generally we can see or exosphere holds all the satellites or most of the satellites orbiting around the Earth. There is another layer of atmosphere known as ionosphere, which isn't having a specific kilometer range of one layer, but it is a combination of three different layers ranging between 60 to 1000 kilometers. So it lies between or from mesosphere to thermosphere and further into exosphere. So it ranges from 60 kilometers to about 1000 kilometers from mesosphere to exosphere. And as the gases in the ionosphere are generally ionized by the solar radiation and form ions, this is the name reason for ionosphere, and it helps us by absorbing the extreme ultraviolet rays. Before we get to define a standard atmosphere, we need to know few basic properties which are defined for atmosphere. And the basic properties are pressure, temperature, and density, which are defined against the altitude change. As we know, atmosphere isn't static; it is totally dynamic, and we can see that it totally varies depending on the location, season, and time of the day. So, if we need to know or define an atmosphere, we need to define few properties, that is the pressure, temperature, and density in as a function of altitude. Before getting into knowing these properties, we need to know about altitudes. There are about six different types of altitudes considered in aerospace. The six different altitudes are named over here as geometric altitude, absolute altitude, geopotential altitude, pressure altitude, temperature altitude, and density altitude. We will get to know about these in subsequent lectures. So, for this session, we will get to know about the first three altitudes. So, what is geometric altitude? If we consider this black circle or sphere as Earth, geometric altitude is the height from the surface of Earth to the point of reference or observation, that is termed over here as Hg. So, absolute altitude. Absolute altitude, as we know, absolute means from zero. So, if we consider the height from the center of Earth to the point of observation, it is known as observation altitude. Why is it important? Because it is important in the cases where we are talking about planetary distances or the distance between two objects. Consider this to be Mars or Jupiter or some other planet. The surface isn't constant, so the distance from the surface cannot be taken as constant, but the center point in turn is constant. So we can consider some the center of Earth, and we can measure the distance between the center of Earth and the center of Mars or center of Jupiter, whatever we are considering or observing. This is the significant role of absolute altitude. So here is a formula of absolute altitude. It's not a complex one, but still, here the absolute altitude is a combination of geometric altitude or geometric height plus the radius of Earth or whichever the celestial body we are considering. The next altitude we are going to see is geopotential altitude. Geopotential altitude is generally termed as h, just h. So it is a fictional altitude measured by considering the gravitational acceleration as constant, and it is playing a major role in literature or whatever numerical we are going to solve, because it is generally considered among all other altitudes. Why is it considered so? It is generally considered because geopotential altitude considers the gravitational effect to be constant, that is g naught, and thus we are considering this. So here we see the formula of geopotential altitude. It is a product of radius of Earth or the celestial body times the geometric altitude divided by the radius of Earth plus the geometric height. So how did we arrive at this formula? Let's get to know about this. Actually, it is derived, and let's get into the derivation part of it. To know about the derivation, we need to basically know two different equations, the hydrostatic equations and the equation of state. Many of us may not know what hydrostatic equation is. It is from basic physics. Still, we can see what hydrostatic equation is. Let us consider a fluid element such as this, having unit area cross section. Let it have a pressure applying towards upwards into the fluid element from below as P, and it consider it to be having a pressure above the fluid element as P plus dP, that is pressure plus change in pressure. And this element is static, that is it isn't moving. So if we apply two pressures, this change in pressure is going to cancel out. So that's it. And the two faces are divided or distanced by a gap of dhg. Hg means the geometric height. So to get the hydrostatic equations, we will just make a summation of the forces in a particular axis. Let us consider the y-axis. Let us just equate the forces in y-axis. Here we see a pressure being applied in the opposite direction, and the sign convention is such that the downward forces are considered as negative, and the upward forces are considered as positive. So with this in mind, let's just solve the equation. So here, first here we have the downward acting force, that is P plus dP. As it is acting downwards, we are considering as negative. So negative sign of P plus dP. And next we have a pressure applied towards the fluid element or in the upward direction. So we are taking it as positive. So this is positive. And the another force which is acting downwards is the weight of the element. So the weight of the fluid element is nothing but mass times the gravity. Mass can also be written as density times volume. As the fluid element is having unit cross section, the area can be taken as 1 cross 1, and the height, there is a particular height and it is not an unit function or unit, that is 1. We are taking the height. So density times the volume, that is length into breadth into height, times the gravity, mass times the gravity. So we will get rho dHg times g, that is gravity. And as the weight always acts downwards, we are taking the sign convention as negative. So when we solve this, the negative pressure and the positive pressure will cancel out, and we will be getting minus dP and minus rho g dHg. That is the differential height, differential geometric height specifically. So when we take this to be equal to 0, the summation of forces is 0 as the fluid isn't moving, we can transfer the minus dP to the right side of the equation, or the left, we can transfer either one of these to the opposite side of the equation. We will get dP in positive, and the remaining term is minus rho dHg. Here rho and g as density and gravity, which are functions of geometric height. The next equation we will be needing is the equation of state. P is equal to rho RT. This is a common equation which we all know. And according to this equation, if we know either two terms of these, we can derive or calculate the third term. That is, if we know the pressure and density, we can calculate the temperature considering the R, that is gas constant, to be a known value. So as we know these two equations, let's get into deriving the geopotential height. So now for obtaining an equation relating pressure, density, temperature, and acceleration due to gravity, we can equate it like we can divide the equation 1 by equation 2, that is the hydrostatic equation by equation of state. So by dividing it, we can see that density terms are constant, so we will cancel out it, and the remaining terms are written as it is. So we get the differential pressure by the pressure is equal to minus gravity, and it is in constant. We need to know that it is a function of geometric height divided by the gas constant R times the temperature T. And here we can see that there are two terms, temperature and gravity, which is a function of geometric height. So the number of unknowns are more, so we need to simplify the equation further. How can we simplify it? So for this purpose, we are defining a new altitude known as the geopotential altitude. As in the previous case, we are having the gravity as a varying function. In this case, we will consider the gravity to be constant, that is g naught, and the height to be transferred as h. So here h means that geopotential altitude. So if we equate both the cases, that is the hydrostatic equation of normal geometric height and the hydrostatic equation of geopotential height, where the gravity is constant g naught and the h is transferred as hg is transferred as h. So when we equate this, the density terms are constant, so we will cancel out them, and the resulting uh, we can also cancel out the negative signs, and the resulting equation is somewhat like this: g times the differential geometric height is equal to acceleration due to gravity is constant, that is g naught times the differential geopotential height. So for obtaining the differential geopotential height or the geopotential height, we can take this z naught term to the LHS, left hand side of the equation, and we get an equation similar to this. So we need to know the g by g naught term in order to substitute in our equation, because g is still a function of hg. For this, we are considering the Newton's law of gravity. Let us consider Earth to be having the mass m, that is greater mass capital M, and we are considering an airplane, so it is having a smaller mass small m. The absolute height between this is the combination of geometric height, that is from surface to the plane airplane, plus the radius of Earth. We know that from Newton's law of gravitation, force between these two, that is the force of attraction between these two masses, uh, is equal to gravity times, that is the constant term g, capital G, the product of masses, that is this mass and this mass, divided by square of distance between them, that is r. So we are considering two cases. In one case, as I said, an airplane is flying at some particular altitude, which is above the surface Earth, that is at some particular geometric height hg. And in the second case, we are taking that a mass or the airplane is still on the surface of Earth, that is the distance between the center point and the airplane is r. So when we consider these two cases, here we can see the change, that is hg plus r the whole square, that is the distance between them, this thing. And the second case, we are considering the airplane to be over here, and here, as it is on the surface of Earth, the distance is considered to be r, that is the radius of Earth. When we cancel out, and we also need to know that in the first case, we are considering the gravity to be varying, and the second case, we are considering that gravity to be constant, because we are considering the gravitational force on Earth is constant, that is surface of Earth is constant g naught. So the force can be written as mass times the gravitational due to acceleration, and here in the second case, the force can be written as mass times acceleration due to gravity constant. When we equate it, we can cancel out the mass terms, that is small m and small m, small m and small m. As a result, we are obtaining an equation similar to this. So when we equate these two, that is divide equation 6 by equation 7, equation 6 by equation 7, we can cancel out the terms, that is g and g is constant, m2 can be cancelled out, and when we are dividing it, we are obtaining r square by, that is equation 6 by this is already in denominator, so it is in denominator, just I have rearranged it. So r square, as it is in denominator, it is again going to the numerator. So we are getting an equation where the g by g naught term is found out as a function of radius of Earth and geometric height, which are known terms. So here we can replace the differential height function with the known terms obtained from this equation. So when we substitute this value over here, we get a similar kind of equation. But here, still, it is the differential geopotential height and it is in the actual geopotential height. So, in order to neglect the differential term, we are integrating on both sides. So, when we integrate on both sides, here the differential and the integration gets cancelled out, and we obtain the geopotential term of or the geopotential height h. And when we integrate the right hand side, as we know, the the integration of x bar n can be written as x bar n plus 1 divided by n plus 1. So here we can see that here it is in the denominator, so we can write it as x bar minus 2. So when the x bar is in minus, so n plus 1, in this case we are getting x bar minus 1, which is written in the denominator instead of writing it as the power in the power terms, and we get divided by minus 1 term, that is n plus 1 term, that is minus 1. So here we it is. So it typically ranges between the surface of a 0 to geometric height hg. When we substitute it, we finally obtain an equation like this, and when we cross multiply it and obtain an equation, we can see that r goes over here and turns into minus r, and this equation turns into r plus hg. So the negative and the positive terms gets cancelled out, and we get just hg in the numerator, and here we and the denominator remains as r plus hg times the radius of r. So here we have an r square taken out as common. So when we cancel out this and this, we get our uh, radius times the geometric height is remaining in the numerator, while the denominator is same as radius plus the geometric height. So this is how we obtain the formula of geopotential altitude. That's it. We have reached the summary of the session. We did know about atmosphere. We learned about altitudes and particularly about three different altitudes, that is geopotential altitude, geometric altitude, and absolute altitude. Thank you. Let's crack Gate Aerospace.